question regarding any issue or from the previous lecture, he can ask me. Okay.
Yes, sir.
Okay, just let me know. I believe, have we discussed this thing, modified slenderness ratio for single angle? And I believe that we have already started design flow chart for compression member. Can you see the slides?
Yes, sir.
या मुझे बताते जाने अब मैं कहाँ से स्टार्ट करना मैंने ये स्लाइड डिस्कस कर ली थी हमने सिलेक्शन चलो मैं दोबारा यहाँ से डिस्कस कर देता हूँ ठीक है अच्छा ये वाली तो हमने डिस्कस कर ली थी ये वाली मॉडिफाइड स्लैंडरनेस रेशियो फॉर सिंगल एंगल
यस सर
सर यहाँ से स्टार्ट करना है कोरिलेशन फॉर सिंगल एंगल यहाँ से
हाँ जी आज ठीक यहाँ से आपने बताया भी था कि ये 40 है लास्ट टाइम ना
जी
ये
सर
80 लिखे ओके ठीक हो गया मेरे ख्याल अब ये वाली स्लाइड डिस्कस कर ली हुई है ठीक है सीआर को लगता है खुद भी नहीं पता उससे भी नहीं पढ़ा हुआ है कोई इशू नहीं अच्छा ठीक हो गया ओके बिस्मिल्लाहिर्रहमानिर्रहीम अच्छा रिकॉर्डिंग भी स्टार्ट कर दें क्या पता आपको सेंड ही करनी पड़ी है हालांकि मैंने डिसाइड किया कि सेंड नहीं करनी
सर ये ओपन ही नहीं होती
ओपन नहीं आपके कैसे होगी आपको यार वो डाउनलोड करनी पड़नी है that are the OneDrive link I'm just sharing the links and by opening that links you can download okay anyhow today we are going to discuss the design flow chart for the compression member okay first of all we have to see that what data is provided so in design of compression member we might be provided with applied load maybe dead load and live loads they may be given separately we may know the length of the member and we may also know the end condition. Maybe the ends are simply spotted, partially fixed or fixed. So depending upon the end condition, we can determine or we can estimate the K value or effective length factor. So we can consult the charts which are provided in LRFD design aid that we have already seen last time. So depending upon the dead load and live load, we can compute the total factored load. So total factor load, we may use the gravity load combination. Dead load may be multiplied with 1.2 and live load may be multiplied with 1.6 and then we may add them both to compute the factor load. And depending upon the end condition, we may know the effective length factor about x-axis or y-axis. So effective length factor may be different about both axes. So if we are dealing with single angle only, in that case, we only need the effective length factor about z-axis. Okay, there was one slide, not there. So last time we have discussed that, maybe I have added one slide, but it's not there. Okay, I will add this slide again. So what I want to say that unlike tension member design, we compute the required area or gross area required from yielding criteria and rupture criteria. So in yielding criteria, we supposed to use the yielding stress because that failure will occur when the yielding at gross area will occur. But in the rupture criteria, we supposed to use the ultimate stress value because the failure will occur when the applied stress will be more than rupture failure. Actually, in this case, uh, I better to maybe derive the equation again for your understanding. So let me add one slide. Okay, the math is not available here, MathCAD. No problem. I have to add maybe the text box. So simple is that we already know that what is the design equation. Design equation is that applied load effect should be less than or equal to phi Rn value. So I have to pick phi value. Alpha, beta. This is supposed to be phi, but this is not convenient.
सर वो एंड पे लिखा हुआ है लेफ्ट राइट साइड पे पाई
इधर नहीं है अल्फा बीटा गैमा। एक्चुअली मैंने अभी ये कंप्यूटर चेंज किया तो उसमें मैथ का ऐड नहीं है, मैं इक्वेशन नहीं ऐड कर सकता, लेकिन एनी हाउ मैं वो अप्रोप्रिएट वैल्यू उसकी सही देखना चाह रहा हूँ।
सर आप पाई ढूंढ रहे हैं ना?
नहीं पाई नहीं ढूंढ रहा, फाई वैल्यू नॉट पाई। मिल जाएगी अभी, इधर आ गई बस, ठीक इसी में ये अभी। यस दिस वन। So phi Rn. Do you already know about this equation? Okay. So phi Rn applied load effect should be equated with the capacity. So Rn is the applied load effect. Applied load effect means that this may be compressive force, tensile force, or bending moment, torsion, shear force, depending upon the case. So in case of our compression member, so our applied load effect may be compressive force or factored compressive force, and then we supposed to compare with compressive capacity phi c Pn. So in this case, if we want to compare, so we know the applied load effect and phi c Pn value. So we can say that phi c Pn value that is actually equal to the phi value, which is strength reduction factor. So load is equal to stress multiplied by area, that may be the gross area, or here in our state structure we representing the stress by F. So F value is the stress value, strength limit. So load divided by area is equal to stress, or capacity will be equal to the failure stress multiplied by the gross area. So it means that if capacity is equal to this one, if I substitute phi c Pn value in this equation number 1, then our equation number 1 will become Pu, I will copy Pu from here, and instead of this I will substitute the value of phi c Pn is equal to area. Actually, we are supposed to compare applied load effect, which is a factored compressive force, with the capacity. In this equation, there is a one issue. Only unknown is the gross area if we know the stress limit. So in case of the compression member, we do not know this F value or the failure stress. because all type of the compression member, they fail at a stress value much lesser than yield value. So we have already seen that if a column fail at a stress value less than equal to 44% of Fy, that column will be regarded as a long column. And if a column fail at a stress value more than 44% of Fy but less than Fy, that is the intermediate or short column. And it means that that failure stress value is not any particular value, and this failure stress is depending upon the slenderness ratio of the column. It is independent of material strength. So it means that instead of writing this F, I supposed to write as a FCR value. So this FCR value, it is a critical stress at which the failure or the buckling in column will occur. So this FCR value is always less than Fy. So this value may be 100 megapascal, it may be 150 megapascal, 200, but we do not know that what is this value. And this FCR value is depending upon the cross-sectional properties which are referred as a slenderness ratio. So slenderness ratio is equal to effective length divided by radius of gyration or minimum radius of gyration. So actually we do not know the section. Section is unknown. We have not designed the member. So it means that we do not know what is the radius of gyration of the column, but we know the length only. So it means that we do not know that what is the failure stress or FCR value of that particular column. But we know that phi C FCR value, this value is depending upon, or you can say that it is the function of slenderness ratio, which is KL over R minimum, or just it is the function or depends upon. So it means that for the start of design, we have to assume some particular slenderness ratio, because in this equation, only unknown value will be the gross area. So gross area required we can determine by dividing the PU value with this phi C FCR value. So it means that if we know the phi C FCR value and we already know the PU value, we can determine how much gross area will be required. And then we can select this section from section properties table. But only unknown value is phi C FCR value, which is the function of slenderness ratio. But we do not know that what would be the slenderness ratio of our designed column, since we do not know that what is the radius of gyration, because radius of gyration is the function of geometric properties. If we do not know the section type or the cross section area, we cannot determine. So it means that in order to start the design, AISC recommends that we have to initiate the design or start the design by assuming some particular slenderness ratio. So there is a guideline. If we want to design a compression member as a single angle, so we have to assume a starting value of slenderness ratio equal to 125. And if we want to design a compression member as by selecting the channel section, then we have to start the design by assuming that slenderness ratio of our intended channel section may be 115. For double angle, and W section, we have to assume the value equal to 90. And for any built up section, maybe double channel, double angle, we have to assume a starting value of 70. And for section which is continuously braced in lateral direction, we have to assume a value of 35. So what is continuous bracing? You may assume that we are having a steel column, maybe any column, and on the both side of the column we have constructed the wall. So this column is lying within the wall. It means that this column cannot buckle due to the presence of the wall on the both sides. So this is referred as a continuous bracing. So depending upon this assumed slenderness ratio, so You can consult the page number 105 to onward, which are given LRF design aid. Can you see these tables? Please respond on
Yes,
screen.
sir.
Okay, good. So these tables are available in LRFD design aid from page number 105 to onward. From 105 to 107, we are having the table for 836 steel. From page number 108 to onward, we are having the table for A50 steel. A50 mean yield stress is 345 megapascal. So these tables are provided or providing us the value of 5C FCR value for different slenderness ratio, starting from 1 to 200. Why 200? Because 200 is the maximum allowable slenderness ratio for compression member. Actually, for 836 steel, we have already seen that critical slenderness ratio is 133. What is critical slenderness ratio? If the slenderness ratio will be more than 133, our column will be regarded as a long column. If the slenderness ratio is less than 133, column will be regarded as an intermediate or short column. For long column, we use the Euler formula to compute the critical stress. So here, this 5CFCR value is equal to 5 value multiplied by 0.877 into Euler stress, pi square EI over slenderness ratio square. So these value has been computed by using the long column and short column formula. So you don't need to use the formula by yourself. So this table has already been tabulated to facilitate the design. For any slenderness ratio, you are provided with critical stress or the stress value at which that column will buckle. So for example, if you are assuming a slenderness ratio of maybe 125 for single angle, so it means that corresponding to that slenderness ratio, you need to select the value of 5CFCR value 111.61. And similarly, if you are assuming slenderness ratio value 90, so you have to take the value of 146.46 for 5CFCR value. So based depending upon the assumed slenderness ratio, we are having 5CFCR value. Okay, now what we may do now, so we know the PU value, we can divide the factored compressive force by the assumed 5CFCR value, we may have our gross area required. So we can determine how much gross area is required. Now our selection will be based upon, we can select this section properties table or column selection table. I will explain this table later. So if we are selecting this section from section properties table, then area of our selected section may approximately be equal to the required area, maybe on plus minus both sides. In tension member, when we are selecting any section, so area of selected section should always be more than required area. But in compression member, the area of selected section may be around 5 to 10%, maybe lesser than the required area. Why? Because our trial section or required area is based upon assumed slenderness ratio value. So it means that any section whose area is marginally less than the required area may also satisfy. So area of selected section should be or approximately equal to required area. So we have to select the minimum section with minimum possible weight among all the available options. Then we have to satisfy the B minimum criteria. Already explained why we have to satisfy B minimum criteria to accommodate the connection. So normally this condition is not by AISC, so we may ignore it. So if the length of the member is between 2 to 3 meters, then B minimum value or the width of connected portion should be more than L by 40. We have already seen if we are connecting uh, the both side of the section, maybe we are providing the bolts or the fastener on horizontal surface, horizontal element and also the vertical, then B minimum should be more than 3.25D plus 18. If we are connecting this section only by one side, then B minimum is 2.5D plus 16, already discussed. And for welded type of connection, we may require minimum width of the section 50 millimeter to provide the weld. And also we have discussed that if, because at the start we do not know that what diameter we are going to use for connection. If diameter is not given, you may assume a diameter of the fastener equal to 15 mm to compute B minimum. Then there is another consideration for the compression member only. So when we are selecting the W section, so for the W section, it is not preferable to select a W section whose depth is more than 360 or 14 inch. So in some special circumstances, we can use a section with higher depth, but in generally most of the cases, we should not select a section whose depth is more than 360. What is the reason? You may see that we are having two sections, both are having same area. One is having the larger depth and one is having the lower depth. The section that will have the larger depth will have less width for the same material. It will have less BF value, less thickness of the web. Or in other words, if the depth will be more, a section will have a very less moment of inertia about weaker axis or y axis as compared to the moment of inertia about x axis. Or in other words, section will have a very less radius of gyration about y axis as compared to the x axis. And we know that a section will always buckle about the axis about which the radius of gyration is minimum. This means that if we are selecting a section with larger depth, it will be more weaker about y-axis. So it will buckle at a lesser load about y-axis. So we want a comparable value of Rx and Ry. Rx, Ry mean radius of gyration about x-axis and y-axis. But along with that, there might be another issue. If the depth will be more, then the web may be thin and flanges they may also be thin. So that may cause local flange buckling and local web buckling. So it is preferable that we should not select a section whose depth is more than 360 millimeters or 14 inch in W section. Okay, after this selection of the section, we may compute the unbraced length about x-axis or y-axis. And in case of the Z section or single angle, we unbraced length about Z-axis. If no bracing is provided, then unbraced length about x-axis and y-axis will be same. But if we have provided the bracing about weaker axis, then unbraced length about x and y axis may be different. We will see these cases when we are going to solve some numerical. So similarly, we may see that or check from the section properties table what are the radii of gyration about x-axis and y-axis, and for single angle z-axis. We may compute the slenderness ratio about x-axis and also y-axis. In case of single angle, we only require slenderness ratio about z-axis. So slenderness ratio about x-axis will be equal to may be computed by this factor or this expression. We need the effective length factor about x-axis. We're supposed to use the unbraced length about x-axis, and similarly we have to use the radius of gyration about x-axis, and same we have to use for about y-axis. So the slenderness critical slenderness ratio will be the one which will be maximum out of these two. If the slenderness ratio is more about y-axis, the section will tend to buckle about y-axis. If the slenderness ratio will be more about x-axis, then the section tend to buckle or bend about x-axis. So maximum value out of these two will be our critical slenderness ratio, that should be less than 200. Okay, now we actually know the slenderness ratio here. If we actually know the slenderness ratio, for the actual slenderness ratio, what you can do, you can check what is the actual phi CFCR value from this table. And if you know the actual phi CFCR value from this table, then you already know the gross area because you have already selected a section, and then you can compute this capacity phi CPN. And this capacity should be more than this PU value, then it may satisfy. Next, if we supposed to design a built-up section, so in case of the built-up section, we know the R value. R value is the maximum value out of these two. So slenderness ratio about y-axis we supposed to use for the built-up section with stay plates. So actually, we need to design number of stay plates, and number of stay plates design is depending upon this value. So again, I supposed to show you the slides that we have already discussed. Yes, the equation was here. No problem. So here, actually, we want to design how many stay plates are required, maybe 1 or 2. So the design of stay plates or number of the stay plates are depending upon this A value. So A is the maximum unconnected portion of single angle. So I told you that we do not want any local buckling or buckling of a single section before the buckling of built-up section. So what we do, we know that the buckling is the function of slenderness ratio. So we keep the slenderness ratio of this unconnected single section portion less than the slenderness ratio of overall less than the slenderness ratio of built-up section. So we already know the slenderness ratio of built-up section. We assume that slenderness ratio of this portion may be less than maybe equal to or less than equal to 75% of the overall slenderness ratio. So we are keeping the slenderness ratio of unconnected portion of single section less than equal to 75% of the slenderness ratio of the built-up section to avoid any local buckling or the buckling of single section within the length of A before overall buckling. So how we can control this? By assuming this thing. So R value we already know because R is the value. Actually, in case of the built-up section, we always use the R value slenderness ratio about y-axis because we need to compute. Sorry, you can take the larger value out of this. I will discuss this later because this will be confusing here. So R value is the larger out of these two values. So we assume K value, we may assume as a 1. So we are assuming that slenderness ratio of single section with an unbraced length of A is less than equal to 75% of R value. So this value we already know. So A is unknown. So what is Ri value? Ri value is the slenderness, radius of gyration of single section. So a single section will always buckle about the axis for which the radius of gyration is minimum. If this single section is the angle, then Ri value will be Rz. If we are making the built-up section with channel, then Ri value will be Ry because single section will always buckle about the axis for which the slenderness ratio is minimum. So Ri value is Rz for single angle and this value will be Ry in case of channel section. So then the selected spacing may be uniform after selecting the A value. So we divide the A value by total length and we can determine that how much spacing is required, and then we can compute the number of stay plates. So the detailed procedure we will discuss in the design example, but here I am just giving you the hint that how we supposed to compute A value. So after computing the A value, we may actually know the A over Ri value. So we may compute the modified slenderness ratio for the built-up section with stay plates. So I told you that whenever we are going to use the built-up section, we require modified slenderness ratio. Why? Because we are not connecting the both section thoroughly, but intermittently at some part. It means that we will not have a fully integral or combined behavior. So it means that in that case, our section will have the capacity at less than as compared to the fully built up section. So to cater this issue, we compute the modified slenderness ratio. So number of stay plates generally are ranging between 2 to 3. Then we check the local stability. So local stability, we have seen that these are the buckling of stiffened element and unstiffened element. So buckling of unstiffened element uh, is the flange local buckling in case of channel and I section, and buckling of legs of of angle section, and stiffened elements are the web of channels and I section. So to avoid the local instability, so lambda value, which is the B over T ratio of our stiffened and unstiffened element, should be less than lambda R value. Lambda R is the limiting value to avoid the buckling in any stiffened and unstiffened element. So lambda R values for any stiffened and unstiffened element is given in LRFD design aid. If you are opening the page number 313 in LRFD design aid, you will find a table. So in this table, you can see that for single angle and double angle with separator. So single angle is having both leg as a unstiffened. Unstiffened mean because they are only connected from one side. In that case, lambda R value is 12.7 for 836 steel. 836 mean that yield strength of steel is 250 megapascal. So we compute the B over T ratio for angle. What is the B over T ratio for angle? Dimension of larger leg divided by thickness of the angle section should be less than 12.7 to avoid local buckling. In case of flange of channel section and flanges of I section, B over T ratio should be less than 15.8 to avoid the local flange buckling. So B over T value in case of channel is BF total flange width divided by thickness of flange. In case of I section, half flange width BF by 2 divided by thickness of flange. And for stiffened element are the web of channel and I section. In that case, B over T ratio value is equal to height of the web divided by thickness of web. So we need to check the local stability, and then at the end we have to check overall slenderness ratio should be less than equal to 200. So here you don't need to use this formula. So I already have told you that if you know the slenderness ratio of your designed column, larger value out of these two cases, you can pick the 5 CFCR value from this table, and this 5 CFCR value is multiplied with the gross area, just like I have explained over here. So you can determine the 5 CPN value. So this capacity should be more than this applied compressive force. So here, so you supposed to compute 5 CPN, that should be more. So if it is a stress reversal member, you need to check the capacity also in tension. So capacity in tension should also be more than tensile force. So at the end, you're supposed to write the design section clearly. And then you will also assume that number of fatigue cycles are less than 20,000 for a design life of 25 years. And if it is a built-up section, we're supposed to design the number of stay plates or lacing and end-tie plates. And then at the end, we have to write the final section using standard designation. So there is another method. We can also select a section from, if you want to design the compression member as a W section. So I will explain this method from these design charts. In your LRFD design aid, along with section properties table, you are provided with W-shaped column section or a table for the selection of column section for W-shape or wide plan. So these tables are provided from page number 111 to onward, just like I have mentioned. So tables is provided from page number 111 to 137. And these pages are referred as a W section table for compression member or column selection table assuming W section. So what these tables are intended to use. So actually in this table, they have only grouped that section which are locally stable. Locally stable mean that BF over T, 2 TF value or a B over T ratio of the flange or the unstiffened element is less than 15.3 and height of the web over thickness of the web is also less than 42.3. So it means that in this table, all the W section, they are locally stable. So I would like to explain this table from any one page. Okay, let's consider this page. Okay, in this table, you will see that we are provided different columns. At the top, if you will see that in the first row, designation or nominal depth of any section is written, which is, for example, in this case, W360. So W360 mean that all these columns belong to a section, W section, whose nominal depth is 360. And in different column, you can see that in the second row, the weight of any particular section is written, which is 122 here. So here the weight of this section is 110 kilogram per meter. So if I am referring, for example, this particular column, so in this column, the designation of the section will be W360 multiplied by 101. So in this column, we are given the properties of section whose designation is W360 into 101. In the same way, this column is dedicated for a section W360 into 64. So here in the third row, the properties in these columns are specified for a 36 steel or for a steel with yield strength 250 megapascal. And if you are looking in this column, so in this column we are provided with the length. variable length, maybe 0, 1.8, 2, 2.2, 2.5, 3 until maybe 13. So if you will read out this very first column, so it is written that effective length KL in meter with respect to least radius of gyration, which is about the y-axis. Actually, for the W section, if it is not braced, so W section will always buckle about minor axis. Minor axis mean that about y-axis. Why? Because it is having less radius of gyration about y-axis as compared to the x-axis. So here in the first column, if we know the type of the section, for example, the first section W360 into 122. For this section, if the section is given, we know the geometric properties. We know the gross area. We know the moment of inertia about x-axis, y-axis. We know the radius of gyration about x-axis and y-axis. So we are provided with all the geometric properties. So if we know the effective length, then we can easily determine the radius of gyration about y-axis. So what does it mean? That in other words, just like I have explained, I can determine the capacity of this section quite easily. So capacity it is not editable. So here, so phi CPN capacity of W section is the function of CR value into the gross area. If we know the designation or type of the section, we know the gross area. If we know the phi CFCR value, we can determine the capacity of that section. It means that the capacity is the function of phi CFCR value which is not known or which is not given, but we know the gross area. But we know that phi CFCR value is the function of slenderness ratio. For this section, we also know the radius of gyration about y-axis. It means that if we know the slenderness ratio of this section, we can easily determine the phi CFCR value. And if we know the phi CFCR value, we can easily determine the capacity of section. So it means that if we are provided with Ry, that is already given, known, because we know its section. Only effective length is not given. So we can develop a table by assuming different effective length. So if I'm assuming effective length as a KL value equal to 1 meter or 1000 millimeter, I already know the Ry value. So if I know the Ry value, I can determine the slenderness ratio. If I know the slenderness ratio, so by consulting these table, I can easily pick the phi CFCR value. So if I know the phi CFCR value, because I know the slenderness ratio, I can easily determine the capacity. So these table, they have been developed because for this section, W360 into 122, we know the gross area and we know the radius of gyration about y-axis. So we are assuming different length. Different length mean that here he has assumed the length 1.8. If we know we are assuming the effective length 1.8, we can easily compute the slenderness ratio about y-axis. If we know the slenderness ratio about y-axis, we know the phi CFCR value. And if we know the phi CFCR value, we can determine the capacity by multiplying with the gross area. So similarly, in this table, different effective length about the y-axis are assumed starting from 0 to maybe 13. And then their respective capacity is written also in their designated column. So here in this column, we are provided with the capacity of W360 into 122 section corresponding to different effective length about the y-axis. And similarly, we are having the capacity value for different section corresponding to different effective length. So actually how this table will facilitate us to select this section. Let's suppose in the design problem, we are given that we need to design a W section which is subjected to a factored compressive force of 2700 kilonewton, and the member is having the length 3 meter. Then we can easily select this section by consulting this table. So what we have to do, because in our data the length of our column is 3 meters, so we will start moving from the back side corresponding to length 3 meters, and I will try to look up the section whose capacity is more than 2700 corresponding to length 3 meters. So this section is having the capacity 2569, so this is not desirable. So this section, yes, this section is having the capacity more than 2700 corresponding to effective length 3. So it means that this will be my desired section. So I don't need to start the design by assuming the slenderness ratio value. I can directly pick the column corresponding to given for example, for corresponding to our given effective length. And it means that my desired section will be W360 into 110. So we will practice this table when we are solving some numerical. So these are the W section column selection table. So here, if you will read out these slides, you will understand this. So load carrying capacity 5 CPN for various W section against the value of effective length with reference to least radius of gyration, which is about y-axis, are tabulated in reference 1, which are given from page number 111 to 137. So corresponding to value of effective length KYLUY, a section may be selected when 5 CPN value capacity, which is given in any column, more than or equal to our factored compressive force. So I will explain this later, this slide, because we are not using this slide at the moment. So here I will stop here. So if you are having any question, you can ask me. So gentlemen, if you are having any question. Okay, Farhan, are you there, Farhan?
Yes, sir.
Okay. Why we have to assume the slenderness ratio value to start the design for the compression member? Anybody who knows the answer can raise the hand, no problem. Yes, Uzair, let me know the answer. Uzair.
सर हमारे पास पहले मतलब हमें पता नहीं होता सेक्शन के बारे में कुछ भी, तो हम फिर एक वैल्यू अज्यूम करके उधर से स्टार्ट करते हैं, फिर सिलेक्शन सेलेक्ट करके और फिर हम उसकी वेरिफिकेशन और कैपेसिटी चेक वगैरह करते हैं.
ठीक हो गया. ओके ओके, माय नेक्स्ट क्वेश्चन इज दैट लेट्स सपोज if I assume the value 115 and I have selected a section is satisfying the capacity check, but it is having the slenderness ratio 130, which is more than assumed value. Will that section will be okay? Will be, can I use that section? Raise the hand.
वो मेरे ख्याल
Raise the hand. Anybody else other than Uzair Shafiq? Other than Uzair, anybody raise the hand? So my question, I am repeating it again. Okay, first, Mohsin, I will ask you the question, but I want to repeat it again. My question is that I have assumed a value of 115 to select a single angle. After selecting the section, I checked out the capacity. Capacity is more than applied load or factored compressive force. It is okay. It is also locally stable. But this section is having slenderness ratio 130. But I assumed that value, I assumed at the start the value 115. So will that section will be okay or not?
सर
Yes.
सेक्शन ओके होगा
Why?
सर वो हमारे जो कंप्रेशन मेंबर की स्लेंडरनेस रेशियो है वो 200 से कम होनी चाहिए और 130 200 से कम है
Yes, yes, okay, it's right. It's mean that our assumed slenderness ratio is just to select a section. So if actual slenderness ratio is more than assumed value, it will not affect the selection of the section if it is satisfying the capacity. Only we have to satisfy that the overall slenderness ratio should be less than 200, section should be locally stable, and the capacity should be more than factored compressive force. So I will stop here. So inshallah, I will see you the next time.